Wireless channel, and today we have another presentation on SMDS-based rigid body localization, which will be given by our dear Niklas Fielding, who just came back from the International Conference on Computer Networking and Communication. So, Nick, please take it away.
Sure. So, hello everyone. Yeah, I will present my paper on, as Professor Abreu said, SMDS-based rigid body localization, which was a collaboration also again with our friends from Continental, David Gonzalez and Osvaldo Gonza. So let's get right into it. Maybe you have seen on our channel before some videos about rigid body localization, and the concept is the same as before. But if you haven't seen the videos, I will introduce the concept again. So if we look here, in normal localization, you always have one goal. You have one target point and you want to localize it. The new thing about rigid body localization is that you don't only have one target position point that you want to estimate, but you want to find a whole body. So in here you can see what we define as the rigid body. In this case would be the car. So on this car, you don't only have one sensor position, but many of them that you know from the manufacturing, for example. So you can see here, we have one car, and on them, I think we have in total of 8 sensors that we call landmark points. So you can see at all the edges and corners of the car, you have the landmark points. And because from the manufacturer, for example, you can assume that we know where all these sensors are placed. That's why we call the initial position of the rigid body the so-called conformation matrix, which is a matrix that contains all the different sensor positions. And now the whole point of rigid body localization is not only to estimate the position of the target, but also the orientation, because before, of course, you cannot do it if you only have one target point. But with the whole rigid body, with the multiple points, you can do it. So what is the concept? So assume you have your rigid body at your starting reference position. That's why we call it S0, which is defined by the conformation matrix, which is then moving by a translation vector. So that's the vector. So it moves from its initial position here. And then it's not only moving, but it's also rotating. So you can see here now, okay, our car first moved to the second position and then rotated. This can be defined by this very simple equation here. So we say now S1 at the first position. If you want to go into tracking later on, this could be time, but we only look at one step basically. So you have your conformation matrix C, which is multiplied by the rotation matrix Q, and then it is moved by this T vector. And so to define it that every point is moved, we have also this vector of ones. This is the main concept that is used in all rigid body localization papers, also in a few of our previous ones that you can see here if you're interested. These are also available on arXiv. Just look for the names and you will find it. Then some more background, context, and relevance. So as I said before, rigid body localization is a technique of estimating both the location and the orientation of a vehicle, which enables high accuracy by modeling the target by multiple points, as you saw. And the nice thing about it is also that the estimation can be performed with various types of information. So you can do, for example, range-based, angle of arrival, but also received signal strength. And of course, where is this relevant? You can do it in indoor and industrial scenarios. So you can model, for example, robots and machineries in smart factories. But just looking at the previous picture, this is, of course, highly important for automotive. So V2V or V2I localization. If you want to go into autonomous driving, this will become very interesting. The main problem, however, is how can the rigid body parameters be efficiently estimated with, in this case, we say distance and AOA measurements, but in general with multiple measurements, because in most of the state-of-the-art and also our own work, the problem was always that we only had one type of information that was used in the localization process. And now the idea was, okay, how can we do it with multiple types of information? So in this case, we use distance and AOA. And the contribution of the paper was first, of course, we introduced this SMDS-based framework for rigid body localization. For everybody who doesn't know what SMDS-based mean. So we talked, I think there's a video where we talked about MDS-based localization, which stands for multidimensional scaling. And SMDS stands for super multidimensional scaling, which was invented by Professor Abreu and his students a few years back. So yeah, this is what we based this approach on. And of course, what I just said, we want to use heterogeneous measurements, so distance and AOA. And then later on, we will also see that the numerical results demonstrate a near Cramer or lower bound performance via Monte Carlo simulations. Then before in the general system model, we saw the car, but in this scenario, to keep it simple, because we will use complex numbers later on, we will just use a 2D rigid body localization model. But the concept is exactly the same. So we represent our model by a collection of n landmark points, but these are only 2D now, so 2 times n. Then we have some known anchor nodes in the environment, which we denote as A. You can see here A1, 2, 3, but of course there can be more. We say we have M in this case. And then we have again a translation vector and a rotation matrix, which is just for 2D now. But the simple equation that I showed before is exactly the same. And also here you can see in the end, we will have some distance measurements, some angle of arrival measurements. In this case, we say, okay, we have all the measurements, but in some of our previous papers, we also talked about the case where we only have incomplete observations. So let's start by talking about the principal idea, and then we go into the actual rigid body localization. So first, if you're not aware, we will shortly talk about multidimensional scaling, the principle. So what you can see here, these are just some nodes and edges in an MDS system. So you have some target points. In this case, they are independent target points. And you have some anchors. In multidimensional scaling, you can see you have these entities, these nodes, where we don't really care about what is a target, what is an anchor. You just have the nodes, and then you will have the distances between the different points. So you can see here a few highlighted, but of course you have all of them. And the main idea of MDS is that you create a kernel based on these distances that can later be decomposed to find the estimate of the positions based on the distances. So here your kernel is simply defined. We won't go into that much detail, but you have this so-called double centering. You have this vector here that does the double centering. You have your distance matrix, and this creates the kernel. But similarly, you can see that just by having the positions of the nodes, you can also create the kernel. So this relation here enables us to estimate the position based on the distance measurements. And how this is done mathematically, here, this is double centered up to the rigid body transform. So how it can be solved via a simple least square approach, let's say. So we can say, given the distances, so the Euclidean distance matrix, you want to find the best locations that X follows this minimization problem where we have the measurements and then this Euclidean distance function. And how this is done algebraically. So again, first you want to construct the double-centered kernel, which you can do by the measurements that you have. And then to find the X, so the position of all the nodes, you can simply decompose the kernel and then solve the problem such that it follows also this optimization problem. This was the MDS example, and now we will move on. Now we will move on to the super MDS. So now the difference is, okay, before we had all these distances between the nodes, but now we don't only have distances, but also angles. So we have these edges, these vertices. And now the kernel is not only defined by the distances, but also by the angles between all the different nodes. But the concept stays pretty similar. So in the end, you again have this edge to coordinate projection. You have your V, which is part of your kernel. Then you have your C and your X. And in the end, you want to, of course, find the position of the nodes again. So the X. Yeah, the matrix coordinates for vectors formed by pair of nodes. And then how the algorithm works, it's pretty similar. You can see again, now we have MDS on the mutual edges. So first you want to construct the kernel again by your distances and the angles. And then you can do the same thing when you found your kernel. You can decompose it, you can calculate the V, and then you can solve it for X. Other than that, the algorithm is exactly the same, but the only difference is that the kernel is much larger because you have not only the distances, but all these vertices now, but they are of the same rank. So now what we want to do in the proposed method, we want to use this approach to model it as a rigid body localization problem where we also have the knowledge of the points between the rigid body. But before that, let me introduce another concept that we need to do that, which is Turbo SMDS, which was published in 2018, where the concept is again similar, but now we say, okay, we have these edges, which we will now model as complex edges. So we will move them from anywhere in space to be a complex number. So we can move them here. But you can see the concept is exactly the same again. So now you have this complex edge, which is modeled by a complex number based on the distance and the angle. And then the kernel is just a little bit rewritten. So you have this complex kernel matrix, which then depends on all the different pairs of measurements. So you have AA, which stands for anchor to anchor. You have AT, which stands for anchor to target. And then you have TT, which stands for target to target. Where in the end, you have your whole kernel matrix here, and you can then divide it into all the different parts. But the question is now, do we really need the full kernel matrix to perform the SMDS? And the answer is no. So what was proposed in the Turbo SMDS was that we only know some part of the kernel. And we only need it because, for example, if you say you have some anchors placed in the environment, then you say you know them already. So we say, okay, VAA is known. And this, how this is written is, the first part is always what you know, so you estimate, and then this is what you don't know. So because we know VAA, it's not placed here, and because of this, we only have some part of the kernel, which is then of interest. And how this is solved is quite simple. You can just rearrange it a bit so you can get an initial solution by the measurements. So K1, K2 comes from measurements, and then you have your VAA, which is known. That's why you can use it for the initial solution. And then you have some VAT and VTT. And then the complete solution is that you iteratively update it so that in the end, VAT and VTT is your outcome, such that you can then fill that in the full kernel to solve for the positions. Now, this was still for independent targets. But what we want to do now is, of course, use it for rigid body localization. So what is the difference between this and the rigid bodies is that now we can assume that we know the anchor to anchor measurements, but also the target to target information, because we said we know how our rigid body is constructed by the conformation matrix C. So in this case, we know VAA, but also VTT. So the only unknown here is VAT. And then the solution is pretty much the same. So we can find an initial solution again and solve it iteratively, which will give us the VAT, such that we can again find the kernel and then find the position of the nodes, which in this case leads to an estimate of the target rigid body landmark points. This is of course nice, but with the position of the target, we don't have the translation yet, and also the orientation. So what do we do next? In this case, just to show the concept, we use a simple least square solution. So we say, okay, now we have this problem. We have the estimates from our SI, which comes from the SMDS. Then what we want to solve for is Q and T, and then the C, of course, is the conformation matrix. So we also know that. And the nice thing about this is we have a closed form solution. So we first find the Q, and then based on the Q estimate, we can find the T. But I also want to highlight that, of course, we can use any method that requires an estimate of the landmark points to find the T and the Q. This was just a proof of concept, basically. Then let's quickly go through the numerical results. So what we do, we have a 10 times 10 meter area with 8 anchor points and 8 landmark points. And to make it a bit more interesting and different from the state of the art, we say, okay, our range measurements are gamma distributed and the AOA are a Tiganov distribution. And then we find the MSE over 1,000 Monte Carlo realizations. And we will have two solutions. The first one is the estimate of the translation, where now we want to compare it to this state of the art, which is exactly what we showed before. So the least square approach. But you can see we have multiple lines here. What does it mean? The first one is the state of the art with distance measurements only. The second one is SMDS with distance only. And the third one is SMDS with distance and angles. What this means is that we can also use SMDS even if we don't measure the angles by simply first measuring the distances and then just use some different state-of-the-art method to estimate the angles. And you will also see that even this will also lead to good results. And then, of course, we also have the Cramer bound for distance and angles. So if we look into it, you can see that the state-of-the-art, the pure distance-only MDS-based, is not so great. If we have SMDS, so we also estimate the angles ourselves, then we can also already see a small gain. But if you really have the distance and angle measurements, you can see that it's much, much better and also much closer to the bound. So the dashed bound is for distance only, and the solid bound is for distance and angles. You can see that it follows it quite well. And then, so this was for translation, and now moving on to rotation, the solution looks pretty similar, but you can see that now using SMDS with distance only gives us a much larger gain already. And then for the full true SMDS version, the proposed method, let's say, it is on the bound pretty much all of the time. So it works very, very well. Yeah, that was it. Then just some take-home messages for you. So take-home message 1, SMDS can significantly improve the performance compared to the state-of-the-art, even if we only measure the distances and not distances and angle of arrival. Then in contrast to most state-of-the-art methods, SMDS-based RBL performs very close to the bound. And as a bonus, as I said, the concept can be applied to any state-of-the-art method that requires an estimate of the rigid body landmark points, because what we get from the SMDS algorithm is just an estimate of the target points. But because this is already so good and much better than the state-of-the-art, the result is very, very nice. Yeah, thank you for your attention. That's it. If you have any questions, go ahead. And if you, the audience, want to read the paper, it's already on arXiv, so you can check it out there. We will also put the link in the description.
Thank you, Nicholas. Nice work. I have one quick question, which is, by virtue of the type of figure that you chose to show, we can't see that usual bump that the MMSE performance has relative to the Kramer bound. Well, if what I mean is that normally if in conventional estimation problems, we have plots as a function of the SNR, we see that the bound CRLB usually doesn't work very well for low SNRs, right? But here you have bounds as a function of the error ranges themselves, and so we don't see that bump. Do you have any idea of how we could do that? Just to see, again, the Kramer bound is known to only work when the errors are sufficiently small that the derivative nature of the bound kicks in, right?
Yeah.
So again, in the context of all the estimation promises happens at high SNR. And here we never see that bump. We never see any region where there is a significant gap between the bound and the actual algorithm. That's what I'm curious about, if you have any inspiring words about it.
So usually we also, even if it's SNR or also the other state of the art, we always showed the results in log scale. So here it's all linear. So maybe if we would show the range error in log scale instead, you could go into more detail for the lower points. Because also in our state of the art, we always go like from 10 to -3 to 10 to the power of 1.
I don't think that is.
No?
No. Well, here's an
know.
idea. For example, if you were to show results only for the angle case, so consider a scenario where you only do angle measurements, and you are measuring the angles, assuming a Tikhonov distribution, but you link the variance of the Tikhonov with the SNR, because there is a relationship between so again, suppose that you are doing this angle estimation using some algorithm, and the SNR of the signal is directly modeled into the corresponding angle errors. Then we'll have a plot as a function of that SNR, And for low SNR, the algorithms just are not able to estimate the angles properly, and so on and so forth, and we might see that bump. I was just wondering if you had an idea of how we can visualize that, because that would be like a confirmation of what is the range of operation that the bound is really
Right.
useful
Yeah.
for. Yeah. But okay,
No,
if
but
you
that's
if
a
you
good
don't
point.
if you
We can think about it. Okay, thank you.
anybody else, guys, any comments, questions?
I have a small comment. So that's the interesting point you raised regarding the Cramer low bound. So I think although in this figure as well, if you look at the comparison between the SMDS for distance only and the corresponding Cramer low bound, you see that when the range error is a bit high, it diverges, right? So like I think this is akin to the low SNR region actually. So maybe if you have a plot in the log scale, we can see this a bit more coming from, because typically you would have a scale going from low SNR to high SNR, right? But this is flipped.
This
So I
is
think
flipped, yeah.
maybe you can see like a small bump in if you extrapolate to like higher range errors as well. And so this is the first point, and then there's another question that I had. So, uh, as seen
Can I
here,
answer
when
to
you
that though? Can I answer to that though? Sorry, yeah, right. No,
yeah,
again, I don't think right that would be the case, because what I see here is that what happens when you have distance only is that if the distances are larger than a certain amount, you start having rigid transformations of your body, right? So, meaning, imagine that you have like a structure made of straws, and you lose rigidity of the structure if the distance that you are measuring are too wrong. So the confidence is too low, then there are different formations that satisfy those distance measurements. That's why you get such a huge gap between the distance only CRLD and the distance only algorithm. You see? Now, when you have both distances and angles, the presence of angles prevents such kind of structural problems, and therefore the bound now comes very close, much closer to the actual achievement of the algorithm. But these two things have nothing to do with SNR as it is, because again, we are already assuming certain levels of errors on the measurements themselves, rather than measuring those quantities as a function of the SNR. That's what I'm talking about.
I see, got
Okay.
it. Okay,
Yeah.
and
Go ahead.
the last concern was, did you try to also use Doppler information? Because by the looks of it, if the more heterogeneous information, the better, right? So you can get probably like an even lower uh rotation mean squared error with like additional Doppler measurements as well.
But Doppler you need for the velocity, right? So
Yes,
this is stationary. If we would do it for tracking or like also velocity information, then yes, we should definitely use Doppler.
I
If you
see.
remember, we did this in one of our previous works, but we didn't use SMDS. So maybe this is also an idea for the future to try that. Good
I
point.
see. But SMDS can be used if you have Doppler information as well, right?
Yeah, I mean, we have other works where we try to also estimate the velocity using SMDS this is the work on the quaternion, where we move to a quaternion and we do
Mhm.
quaternion-based SMDS, and with these extra dimensions, we can add the velocity as estimates as well. But the
I
bounds
see.
here derived could be generalized to it, but that's not the case as I understand it. At the moment, they are all discrete. They are all their own stationary.
I
Yeah,
see. Okay,
true.
great.
Thank you for
Yeah,
the
thank
question,
you.
comments. Anybody else? If not, I thank you very much once again, Nicholas and colleagues, for attending, and let's close this session. Cheers. Bye.